In this video, we're going to apply some of the earlier results that we've seen to extensive form strictly competitive games. One example of such a game is the game that we played as children, Tic-Tac-Toe. So this is a game where you've got two players. The first player uses the character X, the second player uses O, and when it's your turn, you can put an X or an O in any open space. So perhaps the first player puts an X there, the second player puts an O there, the first player puts another X, second player puts an O, the first player puts an X. A player who places 3 of their characters in a row wins the game. Now we've all seen this before, I'm sure, and it's an easy enough game to play. One thing we all learn pretty quickly is that it's not difficult to ensure that there's a draw. So if you're paying attention and you're playing rationally, then you can ensure that you don't lose. And that's going to be relevant, and we'll see why. Let's first write down Tic-Tac-Toe as an extensive form game. What would this game tree look like? Player 1 moves at the initial node. At this initial node, there are 9 different actions that player 1 could take. At the outset, player 1 faces 9 empty spaces and can place an X in any one of those. He can place it in the first spot, he can choose the second spot, and so forth, all the way through the last spot. So there are 9 different choices for player 1 at this initial node. And based on what player 1 does, we end up with 9 different decision nodes for player 2, or 9 different information sets for player 2. And at each one, player 2 faces 8 different empty spaces that he can place an O in. At this decision node, player 2 has 8 different empty spaces. This one, 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 and this one. And so there are 8 different actions that player 2 could take. So when we look at this decision node for player 2, there are 8 different spaces where player 2 could draw an O. And for each of those, we have a new decision node for player 1. And of course, the subgames would be similar at this decision node and this decision node as well. But we won't draw them because it's going to get too big. So let's look at this one, for example, for player 1, the subgame here. At this decision node, player 1 now has 7 empty spaces to draw an X in. So player 1 faces a situation that looks like this, and can put an X in any of the remaining empty spaces. For example, here. Similarly, in this circumstance, they could place an X here. So there's 7 different places where player 1 could place an X. And we carry on in this manner until we end up at terminal nodes. Either there are 3 X's in a row, or you have 3 O's in a row, or you have a draw, where neither of the players win. All terminal nodes are of one of these 3 types. At these terminal nodes, 1 wins, and at these terminal nodes, 2 wins. Of course, player 1 prefers when player 1 wins to drawing, and prefers drawing to player 2 winning. Similarly, player 2 prefers 2 wins to draw to 1 wins. And so clearly this is a strictly competitive game, and we've seen that it's a finite, extensive form game. So what can we say about this game, given what we've learned about such games previously? Because this game is a finite, extensive form game of perfect information, we know that by backwards induction we can always find a pure strategy Nash equilibrium. We also know that it's strictly competitive. Since it's strictly competitive, each player has to be playing a security strategy at that Nash equilibrium. It's not hard to see, if you've played this game, that if you're paying attention, you can always ensure that you don't lose. In other words, you can always ensure that you at least draw. And that means that the security strategy ensures that you at least draw. If both players are at least securing a draw by playing their security strategies, and they're both playing security strategies in the Nash equilibrium, that means that the Nash equilibrium has to be a draw. So just by what we've learned earlier about finite perfect information games and about strictly competitive games, we can conclude then that in any pure strategy Nash equilibrium of Tic-Tac-Toe, the outcome has to be a draw. This type of conclusion doesn't apply only to Tic-Tac-Toe, but it applies generally to extensive form, strictly competitive games. So in general, for any 2-player extensive form game, if that game is finite, if it's a game of perfect information, and if it's strictly competitive, then we know the following. If the possible outcomes, like in Tic-Tac-Toe, or in chess, or in many other games, are that either player 1 wins, player 2 wins, or it's a draw, then either one of the two players has an unassailable strategy to win, and what I mean by that is a strategy that is guaranteed to win, or both players can ensure a draw. However, if draw is not one of the possibilities, then for any of these finite perfect information strictly competitive extensive form games, one of the two players has to have an unassailable strategy to win. So they have to have a strategy that they can play that guarantees that they will win. This result here, it applies to chess as well. So either one of the three following statements has to be true. White can always win, black can always win, or both can ensure a draw. The problem is we don't know which of these three statements is true, because to figure out which of these three statements is true, we would need to solve for the equilibrium. And to solve for the equilibrium, we need to be able to work through the game tree. The problem with a game like chess is that that game tree is very, very large. On average, the game tree is about 80 moves deep, so 40 moves per player. And so any path from the initial node to a terminal node would have to pass through 80 decision nodes. And the branching factor, which is the number of branches at each possible node, decision node, is about 35 on average for chess. So that leaves us with an immense number of terminal nodes to have to analyze. Why is that? Because if you start at the initial node, there are 35 different decision nodes that a player could take. And at each of those, there are further 35 different possible decisions that a player could take. And this thing is 80 moves deep. So if we get all the way down to the bottom, by the time we reach terminal nodes, there are a huge number of terminal nodes. How do we figure out how many terminal nodes there are? We look at the branching factor and raise that to the power of the depth of the tree, which is 80. And recall that if we wanted to do backwards induction, we need to look at all the terminal nodes, evaluate them all, and then work backwards. So we need to look at these 35, for example, figure out which is the best for the player who makes a decision here, and then work backwards. Computationally, that's completely infeasible because there's roughly 10 to the 120 terminal nodes. And that's why we haven't been able to figure out which of those three statements is true for chess. So how do computers play chess? Well, computers use this idea of chess being a competitive game, and the fact that you'll do what's worst for me helps in searching this game tree. Typically, a computer program is not going to search all the way down to the terminal nodes and do backwards induction all the way from the bottom. Instead, how a typical program works is to look at the node that you're at and fix some depth, perhaps 4 moves forward. So suppose I move here, you move here, so I move here, and you move here. So how does the program decide what action I should take here? Well, it goes down the game tree. So it goes down 4 moves, 2 for me and 2 for you. And it looks at all the different configurations that you would be able to choose between for what the board would look like. And it evaluates the board from your perspective. What are the worst configurations among these for me? And I do that for all possible actions that I could have taken at this node. So for all possible actions I could have taken at this node, we look at the set of all the configurations that you could bring us to and evaluate the worst one. And then we just move back up the tree that way. And so why are computers so good at doing this? One thing they do is to use parallel processing, so they can split the tree and send this half to one processor, this half to the other processor. And so that comes in very handy to solve these types of problems. And the other thing is that they tend to have large databases that say whether or not a given chessboard configuration could lead to a win or a draw, and they evaluate the chessboard based on that. So having these access to these large databases and being able to process these trees in parallel is why computers have gotten so good at playing chess. And so searching the game tree and using this idea of min-max, so you minimize my welfare, and I want to maximize, given that you're going to minimize my welfare, is exactly the basis for how computer programs play games like chess.